This video is designed to provide a review for content from Module 2B in my APES class. Module 2B includes information about soil dynamics and resources, and various types of energy, including non-renewable, nuclear, hydroelectric power, and renewable energy resources. Now that we've talked about all of that, let's go back to one important component of the lithosphere. This is soil. Soil is the scientific term for the particles, nutrients, and organisms that make up what is beneath our feet. It is not scientifically accurate to call it dirt. There are 5 characteristics that determine the kind of soil that you're going to get. One of the major categories or characteristics is time. Depending on where you are and the type of rock you're using, it takes hundreds to thousands of years for a single inch of topsoil to form. We also have topography as an issue. Hills versus flat plains are going to impact your weathering and erosion patterns. And it's important to remember that weathering is the process of breaking something down. And that weathering can happen in one of 3 ways: chemically, biologically, or physically. Chemical weathering is typically done with acids. The universal solvent is water. Water is very good at both physical and chemical weathering. Physically, it goes through the process of ice wedging, where water finds a crack in a rock, freezes, expands, thaws, and repeats the process until the crack is wide enough that one piece of the rock falls off. Living organisms can also do the weathering process. This is called biological weathering. They can do it either through physically breaking the rock, such as tree roots, or by secreting chemicals that break down rock itself, such as lichens during the process of primary succession. You also have erosion patterns that are impacted by topography. Erosion is the movement of soil from one location to another, and it's often accomplished either through water or wind. You also have to worry about your parent material. What is the actual kind of rock that you're weathering? The parent material is going to impact the size and type of particles, as well as the inorganic components that form your soil. You also have to think about biological materials. Living organisms provide aeration and contribute to the decomposition process. And climate. Your climate impacts the rates of decomposition, the weathering and erosion patterns, and the kind of degradation you're more likely to experience. Again, think back to that global climate change. When we experience drastic shifts in our climate, we impact not only our weather and our water quality, but also the formation of our soil. It's important to note that in order to understand the kind of soil that you have, you first have to understand what makes up soil. When we talk about particles, we're talking about sand, silt, and clay. And they are in that order from largest to smallest. Sand, because it is very large, doesn't pack very well. Therefore, it allows for more spaces between the particles. Soil that is mostly sand drains relatively quickly and easily. Silt is much smaller and finer. It often packs very well and can make draining a problem. Clay is the smallest and packs extremely efficiently. Soils that are high in clay may take a long time to drain. Once you know the relative percentage of sand, silt, and clay in a soil sample, you can find out exactly what kind of soil it is by using a soil triangle. The key to using the soil triangle is this. Start with the 2 most abundant types of soil. Then read in the direction of the numbers on the triangle. They are angled for a reason. For example, if you had a soil sample that was 50% sand and 30% silt, you would start at the bottom and read diagonally from the 50, and then go to the 30% on the sand and read diagonally down. You should end up with sandy clay loam. This would be your soil type. We also talk about soils in terms of a soil profile. These are the layers of soil if you were to dig down and take a cross section. Let's begin at the very top. The top layer, where you have organic material and dead leaf litter, is called organic layer or humus. Below that, you have the A horizon or the topsoil. This is typically very dark and nutrient rich and where most of your plant roots are. Below that, in some soils, most often those associated with a large body of water, you may find what is called the E horizon, or the zone of alluviation. These are typically silt deposits, and they're not found everywhere. Near those horizons, you will have the B horizon. In a soil horizon that has an E, the E is between A and B. In a soil horizon that doesn't have E, the B horizon is directly below the A horizon. The B horizon is called the zone of leaching, or the subsoil. This is because as water infiltrates and percolates through the soil, it carries nutrients with it. Those nutrients tend to be deposited in the B layer because it is largely made up of clay. It's also very iron rich, giving it a very red or orange color quality. Below the B, you have the C horizon, which is partially weathered parent material. And at the very bottom, beneath that, you have bedrock, which is solid parent material. Now that we've talked about how soil forms and what it looks like, let's talk about its use and degradation. When we think about soil degradation, most of the time we're thinking about agriculture. So these are the kinds of examples I'm going to give you when we look at soil degradation. The first type is called soil desertification, which is the top picture on the left-hand side. Desertification occurs when soil dries out. Extreme drying leads to the appearance of a desert. However, the soil in the area does not actually turn into a desert, as that is a climatological and biological component that doesn't actually happen. However, when soil dries out, it does release carbon dioxide into the atmosphere, which can contribute to the excess greenhouse effect. If you look below at the bottom left, you will see soil salinization. All of that white is salt. When soil salinates, it's most often because of irrigation. Salty water is used most often because fresh water is hard to find. When that water is sprayed on the ground, the water evaporates and leaves the salt behind. Those salts make it very difficult for plants and other living organisms to exist in that soil. If you look at the top middle, you'll see soil erosion. This is most often caused by water. The big problem with soil erosion occurs when there is nothing to anchor the soil, such as plant roots. In the bottom middle, you see waterlogging. This occurs when the water table reaches the top and exposes itself on the surface, and it does so for an extended amount of time. Waterlogging leads to a lack of air being able to be accessed by the roots and causes plants to drown. This also impacts their cation exchange capacity, or CEC, which is the ability of the roots and the soil to exchange cations such as potassium and calcium. On the top right, you'll see soil compaction. This is when large machinery or heavy usage causes the soil to press down and the particles become packed very tightly together. Not only does this make it difficult for roots to have access to air in the soil, it also makes it very difficult for water to infiltrate and drain through. Lastly, you have a loss of nutrient quality. The more that soil is used and the more synthetic fertilizer that is added, the faster those nutrients deplete. So unfortunately, we use soil for agriculture, and the very act of agriculture is destroying the quality of our soil. So it's important to ask, what does healthy soil look like? Healthy soil has an adequate nutrient balance for its area. And when we talk about nutrient balance, we're talking about nitrogen, potassium, and phosphorus. It also has an appropriate pH for the type of soil and the native crops and plants that live there. It is porous, meaning that there is enough and adequate spaces between the particles of soil. And it's permeable. This allows water to infiltrate through and to drain out, avoiding waterlogging. Important to understand when we talk about energy resources is how we classify them. We typically talk about energy resources in terms of their longevity or their ability to replenish and the quality of the energy that we get out of them. Longevity and quality, we end up getting two major components. Okay? We're looking at whether something is renewable or perpetual or whether it's non-renewable. We're also looking at those in comparison with being high quality or low quality. General understanding tells us that renewable or perpetual resources typically have a lower quality when compared to non-renewable resources. They're renewable or perpetual because they can last for a very long amount of time. Perpetual resources are those that are dependent upon the laws of physics, and as long as those laws of physics hold for our universe, those resources will be available to us. Examples of perpetual resources include solar, wind, and hydroelectricity. Renewable resources, which are very similar, can be replaced over a typical human lifespan. The only example of a true renewable resource is biomass, but solar, wind, and hydroelectricity are often lumped in there with renewable resources. Just remember that there is a slight difference. Even though they are more renewable, that doesn't necessarily mean that they have a high quality. They're considered low-quality resources because they are very dispersed or they do not produce high amounts of energy per unit of the resource. This is largely because they're not available in every location around the planet, which makes them inefficient and oftentimes expensive. Non-renewable resources, on the other hand, are often equated with being high quality. Non-renewable resources, such as nuclear or fossil fuels, have finite amounts and they can be used up. They require millions of years to replenish, so once we've exhausted our resources, it's going to take a very long time for them to come back. However, it's high quality because it's concentrated, and they produce high amounts of energy per unit of their resource. And when we talk about non-renewable resources, we're talking about minerals like uranium and fossil fuels. Here are the examples of the most common non-renewable resources. You'll notice by looking at the chart that 3 of the 4 are hydrocarbon-based. This includes coal, petroleum, and natural gas. All of our non-renewable resources that are hydrocarbon are typically associated with areas of ancient bogs or forests. These are places where we used to have large amounts of biomass, including fern forests and dinosaur habitats. Coal comes in 4 major types. Coal is peat, anthracite, lignite, or bituminous. These are the 4 types, but not necessarily in the exact order of least to best. The least efficient type of coal is peat. The most efficient type of coal is anthracite. In the middle, you have lignite and then bituminous. Petroleum is often crude oil, tar sands, or shale oil. And natural gas can vary by its composition, but most often it's methane. Nuclear material, or elemental uranium, is what we use for nuclear reactors. While we typically use uranium-235, it is possible to use uranium-238. This map shows you where coal resources are found across the globe. The reddish yellow tells you where anthracite and bituminous coal are found most abundantly. Remember, these are the 2 best forms of coal. The green shows you where lignite is. And remember, lignite is just a step below peat. If you look at the reddish orange, you'll notice that it's majorly concentrated in Russia and parts of the United States, particularly the Appalachian coal belt. However, you do also find it in some abundance in Australia. Russia also has large deposits of lignite, most of which is found in Siberia, but can be used in order to produce electricity and other resources. For this reason, when we talk about the abundancy of coal, the two major players we're talking about are Russia and the United States. This map shows you where oil is found in abundancy across the globe. You'll notice that 66% of our known petroleum reserves is found in the Middle East. This includes countries like the United Arab Emirates, Saudi Arabia, Iran, Iraq, Kuwait. There are multiple countries in the Middle East that have joined together to create basically a monopoly when it comes to petroleum. That monopoly is called OPEC, OPEC, or the Oil Producing and Exporting Countries. The Middle East has the largest known reserves of oil across the globe. Next up, you'll find some in Central and South America, most often associated with Brazil. You see some in Africa and in the former USSR, but not large amounts. North America, particularly the US, has some oil reserves, most often in Alaska and Texas, but they are typically difficult to get to, and there are other issues, especially in Alaska, with wildlife reserves being on top of those oil reserves. Discusses where you might find natural gas. One thing to remember is that natural gas often co-occurs with other non-renewable resources, most often petroleum. So it shouldn't come as a surprise that the Middle East has a large cache of natural gas resources. However, you also see it in Russia, particularly northern Russia up towards Siberia. The US has some, but not nearly as much as the Middle East and Russia have. Finally, this graph shows you where we would find elemental uranium that we can use in nuclear generators. Here, the darker the color, the more abundant the resource. And while parts of Canada and parts of Russia have a relatively high abundance of uranium, the vast majority of our uranium for nuclear power comes from Australia. So not only do the animals in Australia want to kill you, the rocks do too. So to this point in the course, we've talked about how the burning of fossil fuels contributes to global climate change. So maybe at this point you're asking yourselves, why do we use fossil fuels? Well, here's a general list. They're easy to access and to refine. And they're accessible. They're abundant. They produce a high quality of energy per unit of the resource. They're compatible with our current energy technologies. For the most part, they're reliable, and they're easy to store. You'll notice that there is an asterisk next to easy and abundant. This is because they are easy and abundant right now. But there will come a point when it is very difficult to find these resources, and it will cost more money to access and transport them than profit would be getting out of using them. So those are the reasons why we would. Why would we not want to use them? Well, they're limited in their amount. They're non-renewable resources. We're rapidly reaching the point called peak oil, where it becomes more financially detrimental to try to find the resource than it would be to try to find it and sell it. It obviously contributes to greenhouse gas emissions and other methods of environmental pollution. But they're also politically and economically strategic, particularly for those countries who have a monopoly on them. The United States dealt with two of these, one of them in the 1970s with the oil embargo. The Middle East stopped shipping petroleum to the US, and we had a drastic run on gasoline. A year or so ago, a large majority of the Saudi Arabian oil fields were actually on fire. Having them concentrated in one place and then having the countries who trade them not get along makes it very difficult for us to say that fossil fuels are a good idea, because we're politically and economically dependent on those places that have them and are willing to share them. So this graph discusses what peak oil is. And peak oil is the idea that there will come a time when it is more expensive to find, attain, transport, and use a resource than the profit would be getting out of it. So as you'll see here, it shows that peak oil would hit right around the mid-2010s, maybe about 2011, 2012. The thing to think about is we're now in 2020, and we have surpassed the predictions for peak oil. So what does this mean for us? We don't quite know yet. But we're reaching the point where it's going to be very difficult to find new, proven reserves of petroleum, coal, and natural gas. So how do we use our energy resources? Particularly, how do we use fossil fuels? This graph compares energy resources from 2011 to 2040. As of 2011, over 75% of our energy resources came from fossil fuels. When you add in nuclear power, we're talking almost 85 to 90% of our resources are coming from things that we're going to run out of. In 2040, we'll see that number stay a little bit lower. Just over about 75 will come from our fossil fuels, but a large number of it's going to be coming from nuclear power now. We're also opening up our biomass and other renewables. But unfortunately, by 2040, when we all should be driving flying cars, we're still going to be burning fossil fuels. That is, if we can still find them. So we've talked about energy resources. We've talked about quality, and we've talked about longevity, but we haven't really talked about how we actually get the energy from a non-renewable resource. Let's talk about fossil fuels first. We obtain coal, oil, and natural gas, and we burn them. When we burn coal, oil, or natural gas, it produces heat, and that heat is used to boil water. The boiling water produces steam that is put under high pressure in a narrow pipe. That pipe moves the steam where it releases it onto a turbine. The turbine spins, creating mechanical energy. The turbine is connected to what's called a generator, and the generator takes that mechanical energy and converts it into electrical energy. That electrical energy is then put on the grid and is made available for us to use. What are the problems associated with fossil fuels as an electricity source? We've already talked about some of them, but let's drill down to the big ones. The greenhouse gas emissions are amazingly vast from fossil fuels, largely because most fossil fuels don't combust completely. Incomplete combustion produces carbon dioxide as a byproduct. Additionally, there are impurities in all of these resources. Most of those impurities come in the form of nitrogen or sulfur compounds, which means when we burn the resource, we're releasing most often nitrogen and sulfur oxides into the atmosphere. Both of those are major air pollutants and can lead to issues such as acid rain. Fossil fuels also produce particulate pollution, which are very small, fine pieces of dust, for example, that come off of coal burning and get into the atmosphere. You can get that in your lungs, and it can cause major health defects. And lastly, if we're burning coal, we have ash that's left over. It doesn't burn away to nothing, and that ash has to go somewhere. Most often it's put into coal ash pits, which are lined with plastic and left alone. We have problems of water infiltration and the collapse of those liners, such as what happened in the Dan River a few years ago. Nuclear energy. We talked about fossil fuels. Let's talk about the last remaining non-renewable resource. Nuclear energy comes from the process of nuclear fission. Nuclear fission occurs when an atomic nucleus is bombarded by high-energy neutrons. That high energy neutron splits the atom into two smaller atoms and releases other neutrons, which eventually cause a chain reaction cascade that produces vast amounts of energy very quickly. Nearly all nuclear power plants around the world use nuclear fission. This is because nuclear fusion is greatly energy intensive. It requires very, very high amounts of heat and simple energy to fuse two nuclear atoms together. So, nuclear fission is the way we go. So why do we use nuclear energy? The pros are pretty straightforward. There's little to no impact on the greenhouse effect. It doesn't produce carbon dioxide. However, it does produce water vapor. It's a reliable source of energy. We know how nuclear energy works, and we have a pretty refined system of figuring out how much energy we can get out of a certain weight of nuclear materials. It's useful as a transition from fossil fuels to renewables as well. Because we have a very good idea of how much energy it's going to produce, we know how long it's going to be able to last as we start to transition our technology from fossil fuel based to renewable based. And it can produce a lot of energy. Unfortunately, there are some downsides to using nuclear energy. One of the things that it has massive amounts of thermal pollution that are produced. Thermal pollution is just really hot water that's often dumped into local bodies of water that can drastically change the way in which the organisms live. Again, this thermal pollution can also come in the form of steam or water vapor, which is, as we know, one of our greenhouse gases. It also produces radioactive waste. This waste and the contact water have to be stored indefinitely and separately. Nuclear energy resources and nuclear energy power plants are expensive to produce, maintain, and decommission. And they are subject or susceptible to industrial sabotage or terrorist attacks. So what does a nuclear power plant actually look like? And what are the pieces you're responsible for knowing? So let's talk through those really quickly. You'll see here a list of locations matched with an image. Only the letters that have a star next to them and are listed underneath are the ones you need to know. So let's start at the beginning. A shows us the containment structure. This is a large concrete dome that is used to house the part of the reactor that's actually doing the nuclear reaction. Within that reactor core, you have B, the control rods. Control rods are made up of a neutron-absorbing material, most often graphite, that can be raised or lowered to change the rate of a reaction. When the control rods are lifted, the reaction moves quickly. When the control rods are lowered, those neutrons are absorbed by the graphite and they don't reach the atomic nuclei, and therefore the nuclear fission doesn't happen. Within that reaction center, you also have K, which are your fuel rods. And the fuel rods are typically made up of stacks of small pellets of a uranium resource. Sometimes we have your enriched uranium, which makes the process happen faster. While the uranium is most often uranium-235, you can also use small amounts of uranium-238. Also housed in the containment chamber is D, the steam generator. In this container, heat from the reaction is pumped through a body of water. That water heats up and produces steam, which is forced through E, the steam line or the steam pipe. That steam pipe forces the steam over H, which is the turbine. The turbine produces mechanical energy and is connected to G, which is your generator. The generator takes that mechanical energy, converts it to electrical energy, and puts it onto the grid. The steam that moves across the turbine now condenses into water. Some of that water is moved into what's called the cooling tower, which you'll see as J. This cooling tower allows excess heat to be removed from the water and the steam in order to be able to put the process back through again and then release some water as needed. It's not as hot as it could be, but it's still pretty hot. It's also important to note that around the fuel and control rods, you also have water. This is called contact water. It's important because it helps to maintain the temperature of the reactor core, but it also makes the problem of having to be stored separately because there are impacts on water when it goes through nuclear reaction. We get energy from nuclear resources. Well, it's very similar to how we get energy from fossil fuel resources. The only difference is that instead of burning a fossil fuel, we're going through the process of nuclear fission with uranium-235 or 238. That uranium is bombarded by neutrons, causing a chain fission reaction where the nuclei split apart. Heat from the fission reaction is used to boil water. The boiling water produces steam that is put under pressure in a small pipe. The high pressure pipe puts the steam on the turbine, which spins and produces mechanical energy, which is then connected to the generator, which produces electrical energy. The process is very similar to what you're going to find in the majority of our resources. So if you can remember turbine to generator, you have at least 75% of the energy generation process. So how are nuclear plants decommissioned? Okay, this happens with reactors that are no longer in service, either because their technology is out of date or the company running them simply doesn't want to run them anymore. It requires the removal of all the radioactive material to perpetual storage. That perpetual storage almost always takes place in a salt mine. This is largely because salt mines are geologically stable, they have plenty of open space, and they're far away from people so that the nuclear material doesn't really get messed with. When we talk about radioactive material going into perpetual storage, we're talking about the spent nuclear material, so the uranium, as well as the contact water from the reactor. The contact water can sometimes form what is called heavy water, which is water that is filled with deuterium atoms. And heavy water is a component for nuclear weaponry, so we have to store it carefully. Then we have to stabilize or reinforce the empty reactor. This often happens through re-encasing the containment chamber with lead-lined concrete. And there are 3 types of decommissioning, and this typically depends on how early in the process it happens and how long it generally takes. Early decommissioning takes 5 to 10 years. Safe enclosure takes 40 to 60, and this is the most common one. And then entombment is when we keep the radioactive material on site and we encase the entire reactor in lead-lined concrete. The thing is, whatever type of decommissioning we do, that's not the end of the process. Regular maintenance and security has to take place to ensure that there are no problems that could cause material to leak into the environment. It's always possible that something got overlooked or something got left behind. So regular maintenance and security is important to maintaining the safety, not only of the plant, but of the people who live nearby. So what are the general problems associated with nuclear power? We addressed a few of them, but let's look at the big ones. First of all is thermal pollution. This is the release of hot water into a local body of water. This often causes massive algae blooms, bacterial growth, and changes in aquatic ecosystems that can lead to mass fish kills, largely because the water is too warm for the organisms that are adapted to the zone of tolerance there. We also have water vapor released from the cooling tower. While it's not carbon dioxide, water vapor is a major greenhouse gas, so it does have an effect on our global greenhouse effect. You also have the byproduct of radioactive waste that has to be stored indefinitely, and it's stored by impounding. In the US, a good amount of nuclear material is impounded at Yucca Mountain. And lastly, there's the production of heavy water. This is a requirement for the production of atomic weaponry. So when heavy water is produced, it's something we have to take very seriously. And we have to maintain and protect it very particularly. All right, we've finished the non-renewable resources. Let's start talking about perpetual and renewable energy. Remember that the difference between renewable and perpetual is that perpetual is a very specific type in which it is dependent upon the laws of physics. And as long as those laws hold true, those resources will be available for us. The only true renewable resource is biomass. But remember that the perpetuals are often lumped in with that. So here are your major types of renewable energy resources. We're talking about biomass, coming in solid and liquid forms. Hydroelectricity, which can be in the form of a run-of-river, an impoundment dam, or tidal and wave energy. We have solar energy that can be either active or passive, hydrogen, geothermal resources, and wind power. So when we talk about biomass, one of the things that comes up is this idea of being carbon neutral. To be carbon neutral, you're typically a plant. Plants go through the process of photosynthesis, which removes carbon dioxide from the atmosphere and uses it to produce sugars that are sometimes used to produce the actual mass of the organism. When that organism is burned, for example, as a tree, the amount of carbon that's released is most often equal to or slightly less than the amount of carbon dioxide that was removed from the atmosphere during that plant's lifetime. This means that its net carbon emission is basically zero. When we talk about biomass, we're talking about two general categories, solid or liquid. Solid biomass comes in the form of wood, charcoal, or animal manure, all of which are most common energy resources used by individuals in developing countries. Then you have liquid biomass, which is ethanol, other biofuels that can be used in what's called a flex fuel vehicle. Flex fuel is traditional gasoline mixed with ethanol, and cars that are newer than 2014 can often use flex fuel. Hydroelectricity is the process of using moving water to produce electricity. And there are four major ways we can do this. We can do this through what is called a run-of-river turbine, a traditional impoundment dam, tidal energy, or wave energy. Run-of-river hydropower is basically the simplest version. In the very simplest form of run-of-river, you typically take a small turbine, place it in the fastest moving part of the river, and connect it to a small generator on the bank. This is most often used by individuals who want to live off the grid and produce their own electricity. You can also, however, divert small amounts of water to run over a turbine, which is connected to a generator to produce electricity. This is relatively inefficient, and it only powers a small amount of materials at any given time. So this is what you most commonly think about when you think about hydroelectricity, a dam. This is an impoundment dam, and they're most often made of large blocks of concrete and associated with large river systems, such as the Colorado River, which houses the Hoover Dam. There are several major components of an impoundment dam that you should know. You should be familiar with the reservoir, which is the water that is held behind the dam. The intake, which is the area at which water from the reservoir is able to enter the dam system itself. You have the penstock, which is the actual tube that moves water from the intake into the turbine. The water flows over the turbine, spinning it to produce mechanical energy, which is then run through a generator to produce electrical energy. There are some problems with using an impoundment dam, and the biggest of those are changes to the environment. The area behind the dam is flooded to make room for the reservoir, and oftentimes you have deposit of silt in that reservoir, which makes it shallower and shallower as time goes on, meaning overall you're going to get less energy over a longer amount of time. Hydroelectric dams also displace a lot of people. They're very expensive to build, but not very expensive to maintain. But you lose a lot of natural resources and you lose a lot of homes for people. On the far side of the dam, you also have problems with diversion of the river and a lack of water to ecosystems and organisms downstream. It's particularly a problem when you have things such as anadromous fish, or fish that are born in freshwater, live in saltwater, and then come back to reproduce in the freshwater. The best example of this is a salmon. These organisms need to be able to move through the river to reach their spawning grounds, and sometimes dams get in the way. There are several laws on the books that require dams that are in the way of a fish migration pathway to have what is called a fish ladder, which is areas set aside for the fish to actually be able to jump all the way up to the top of the reservoir. This is an example of a tidal energy production. Tidal energy comes from the movement of tides in and out during the morning and the night. Tidal energy, therefore, is only useful twice a day. In order to get the energy from tidal movement, a turbine is placed near the bottom of the ocean near the coast. As the tide comes in, it turns the turbine one way, which is connected to a generator to produce electricity. When the tide moves out, it spins the turbine the opposite way, which produces mechanical energy to produce electricity. Remember, tidal energy is lower down in the ocean, and it's only helpful twice a day. Wave energy, however, is a little more constant. This is gathered by putting a paddle or some kind of floating buoy on the surface of the water. As this floating buoy or this paddle moves up and down, it actually moves a series of springs and connected levers that spin a turbine. That turbine then is connected to a generator to produce electricity. Wave power can be useful, but they're typically expensive and some people don't like to see them because they ruin the majestic vista of an ocean coast. So let's talk solar energy. There are two major categories of solar energy: active and passive. Active solar energy actually uses the energy from the sun to do something specific. For example, we can use energy from the sun for solar heating. We can also use it for electricity through photovoltaic cells and solar thermal power plants. But there's also passive solar energy, which comes in heating by using building design and solar ovens. Demonstrates where solar energy is going to be most efficient and most abundant. We know that solar energy is more completely directed closer to the equator. Therefore, the further close to the equator you are, the more likely you are to have direct access to sunlight and have more efficient solar energy. You also want areas that are open and don't have a whole lot of trees or buildings to block the sunlight. Because of this, areas in the southwestern United States are the best for using solar energy. However, it can be used in other places. It's just not as efficient as it would be in those particular areas. Here you see examples of active solar energy. Let's start with the image on the left. This shows a photovoltaic cell on the roof of a house. That photovoltaic cell uses photons from the sun to directly produce an electrical current. That current is then moved into a DC to AC converter and added to the breaker box. In some places, this solar energy can be directly used in the house. In other places, like North Carolina, the solar energy has to go onto the grid and then be given back by the power company. The image on your right shows solar heating. The process is very similar, except we're not using a photovoltaic cell to produce electricity. What we have is a panel on the roof that pumps water through it. Cool water is pumped in, warmed by the sun, and then warm water is pumped out. It's typically used for a water heater to reduce electricity bills. Here is an example of a house that is designed with passive solar in mind. Note that we talked about how the solar energy is more concentrated at the equator. So regardless of where you are, orienting your house and your windows toward the equator will make your process a lot more efficient. In the northern hemisphere, for example, we would face windows south. The opposite would be true if we were in the southern hemisphere. You'll notice that this house has a lot of different pieces that can make solar energy useful. It has a skylight and high efficiency windows that have overhangs on them. There are trees planted in specific places to help reduce the glare of the sun during the summer. It's also well insulated and has higher efficiency heating and cooling systems. How does passive solar actually work to help you reduce your energy bills? The design of your house makes a big piece of this. The sun, as we know, changes position in the sky as the Earth moves around it in its revolution. During the summer, the sun is higher overhead and produces a ray that's a little more perpendicular. In the winter, however, the sun is lower in the sky and that angle isn't as strong. Basing your overhangs on this difference in angle of the sun, you can produce houses that allow the winter sun to come through the windows, most often windows that are double paned, allowing for an area of insulation in between. This winter sun can help to brighten your house and can produce some heat, especially if you have heat trapping floors. Over the summer, however, the overhang is at just the right position to block the majority of direct sunlight coming in, which can lead to lower cooling bills because your house gets not as hot. You can also use energy from the sun to cook things. You can have a traditional solar oven, a panel cooker, or in some big cases, a parabolic solar cooker that uses parabolic mirrors to focus the sun's energy on a very specific place. It does take longer to cook with a solar oven, depending on what you're making. And as always, it's going to be more efficient and faster the closer to the equator you are, and the more direct your sunlight is. Wind energy. This graph shows you the global installed wind energy capacity by gigawatt per year. You'll see that from 2000 to 2016, we made massive gains in the amount of energy we're getting from installed wind energy. The hope is that this will continue to rise. However, there are some problems associated with using wind energy. One of those being that it doesn't always work in every place, and there are storage problems associated with it as well. These graphs compare the wind capacity to the percentage of energy gained from installed wind. It's interesting to note that the areas that have the highest wind capacity are actually the ones that use it the least. In this case, you'll see that China has the highest installed wind energy capacity, but actually the lowest percentage of energy that's coming from generated wind. Denmark, however, has the lowest capacity, but it has the highest percentage because it has invested in efficient technologies and using its land in appropriate ways. Additionally, it's also important to notice that Denmark is largely single race and a smaller population compared to China or the United States. So, how does a turbine actually produce electricity? One thing to make sure you note, a wind turbine is used to produce electricity. A windmill is used to grind grain into flour. So when we talk about a wind turbine, we're talking about most often the blades and the nacelle. These are the pieces at the very top that are at the center of producing the electricity. The blades are attached to a rotor, and the rotor helps to maintain what's called the pitch of the blades. The pitch is the angle of attack, or the angle at which the blade is turned into the wind. Most often, the best energy is produced when the blade is pitched between 12 and 15 degrees, depending on the amount of wind and the strength of the wind. The blades are also designed to shut down if the wind becomes too strong. 85 miles an hour is typically the limit for most of these wind turbines. The blades will shut down and actually all fall to be next to each other at the very bottom of the rotor. The blades in the rotor are attached to what's called the gearbox, and this is housed within the nacelle itself. The gearbox serves as the turbine piece. It takes the mechanical energy of the spinning of the turbine and moves it through to the generator. The generator produces the electricity, and it gets run down the entire system and put onto the grid. These things can be ridiculously tall, some of them 250 feet high. They're very well equipped to do what they're designed to do. However, there are some problems associated with them. Wind turbines can get in the way of bird and bat migration. Bats are also strongly attracted to these because bats use echolocation. And the purpose of echolocation is to find a moving object that it might perceive as prey. When the bat uses echolocation that bounces off of a wind turbine, the bat will fly into it, and sometimes the wind turbine wins. In North Carolina, there's also problems with wind energy. North Carolina is not a wind-friendly state. We do have one of the largest wind farms on the eastern coast down near Elizabethton, but that's only because it was grandfathered in before some of the laws were created. One of the important laws is the Ridge Law, which prohibits the building of wind turbines on mountaintops. Additionally, you have House Bill 486, which made it impossible for land or off-coast wind turbine farms to be produced. However, the makers of the Amazon East Wind Farm are working with the federal government to create a wind farm just off the coast of North Carolina in United States water, where North Carolina doesn't have a say. Most people say that the problem with wind turbines is that they're loud and that they're an eyesore. Having seen them myself, they're actually not that loud, and they can be integrated well with various types of land use. I don't think they're really that ugly. They're actually really cool. Geothermal energy requires areas to have high amounts of easily accessible heat from the center of the earth. This comes in the mantle, and it's most often found in areas that are geologically unstable. So if there are volcanoes or earthquakes nearby, geothermal energy is a good resource to use. The major way that geothermal energy is used is by putting pipes into the crust and running water through them. Cold water is pumped through, it is heated by the heat from the inside of the earth, and then the warm water is pumped back out. That water can be used to heat your home, including heating your floors, or be used as part of your water heating process for showers, dishes, and laundry. Hydrogen energy is something that is new, and we most often talk about it when we think about cars, hydrogen fuel cell cars. The major thing that happens here, and what you need to know, is that the hydrogen is actually derived from water. Water is put through a process that splits it into its hydrogen and oxygen compounds. And then the hydrogen is then combusted to produce the energy. It's a little on the experimental side, and there haven't been a whole lot of hydrogen fuel cars or other resources produced at this point, largely because there are some substantiated and unsubstantiated safety concerns. And also because the system that we have now isn't necessarily as efficient as it could be. We have efficiency. Let's talk about this thing called EROEI, or Energy Return on Energy Investment. In order for a resource to be considered viable, it has to have at least a 1-to-1 energy output. The energy out needs to equal the energy in. In order to be economically viable, we're talking a 3-to-1 ratio. The highest that we know of is large-scale hydroelectricity, which actually has an EROEI of 100 to 1. But EROEI is not enough when we try to decide whether an energy resource is useful for us or not. We have to keep in mind where we are, what our energy demand is, how many people we're trying to serve, and do we have the storage capability for this resource to be able to be used consistently on the grid? That's the major problem with solar and wind. It's not consistent. And we don't necessarily right now have the capability of storing the electricity that comes from a wind farm or a solar farm. We also have a grid that is severely outdated. The grid we have now was designed for fossil fuel use. One of the things we need to do is update to more smart grids that are able to use variable energy resources, such as solar and wind.